This video is to help you understand how to assess normality of a data set, specifically normal probability plots on your calculator and how to interpret them as well. So the following data are the serum cholesterol levels of 50 men ages 38 to 41 years old who participated in a study done several years ago at the University of North Carolina in Chapel Hill. What I would have students do at this point, and if you'd like to pause the video and try it for yourself, that'd be great, is to construct a box and whisker plot on your calculator. How would you describe the distribution? Then find numerical summaries of the dataset. Does the dataset appear normal? If so, using your numerical summaries, assess whether or not it really is approximately normal. The student's mission at this point is to try and prove it. Now, I haven't explained to them how to check for normality. I just want them to kind of investigate as a group or partners in order to use what they know and try and prove this point. Now, this is what your box and whisker plot should look like along with numerical summaries on your TI-84 calculator. Now, a couple things to notice in terms of the numerical summaries that help support the symmetry characteristic of the data set. First of all, notice the mean and the median are fairly close to each other. The mean is 224.9 and the median is 224. That is a characteristic of symmetry. Also, notice the distance between Q1 and the median is similar to the distance between the median and Q3. That also is a characteristic of symmetry. So these are a couple things that I can tell from my numerical summaries that haven't necessarily proven normality, but they're definitely supporting the concept of possible normality, specifically the characteristic of symmetry. Now, one way that students can check whether or not it's approximately normal is they can check whether or not the data follows the 68, 95, 99.7 rule, also known as the empirical rule, or I refer to it as the radio rule. So sure enough, if I break up my data, the mean according to my calculator is 224.9, and my standard deviation was 43.69. So if I actually take that mean and I go out 3 standard deviations in each direction, and I identify those values along this axis, I can simply count the data in terms of how many values fall in each section of this distribution. So if I went through the data and I counted how many values fall between 93.83 and 137.52, I only tallied one value to fall in that interval. I tallied 7 values to fall in this next interval, 17 in the next, etc. So you can use this rule and count the values versus the total sample size of 50 and see whether or not these percentages stand up. So I should see approximately 68% of my data within this plus or minus 1 standard deviation. I should see about 95% plus or minus 2 standard deviations, etc. So I end up actually observing 74% within 1 standard deviation, 96% within 2, and 100% within 3. So even though these proportions do not match my empirical rule exactly, they are fairly close, and I can probably assume at least approximate normality. Now, while experience can suggest whether or not a normal distribution is plausible in a particular case, it's extremely risky to assume that a distribution is normal without actually inspecting the data. So that's why I've identified there's 3 different ways to say that data is normal. 3 different ways, some are easy and some require a little bit more work on your part. The first and easiest way is if the data or population is stated to be normal in the problem. Now this is ideal. This is the easiest for us because we aren't required to make any sorts of graphs or assumptions. If it tells me either of these things are true, in fact that they are normal, it's important to identify the shape as being normal and not being approximately normal. The next is if it's not stated within a problem, but you're given the data, you can graph it and try and assess whether or not it's approximately normal. Now the last one requires the most risk. If it's not stated in the problem and you're not given the data, you have to assume it and proceed with caution. Now by assuming it, you're simply identifying the fact to the reader that while the data might not technically be normal, therefore your calculations might not be accurate based off of that assumption. I always say the phrase proceed with caution because it identifies the fact that I'm aware my calculations might be off if normality isn't true, and I'm simply identifying that case. So we have a few methods for assessing normality. I already showed you how to use kind of the tally method. Method 1 included constructing some sort of graph to check if normality seems reasonable, graph and look. Now method 2 is a little bit different. It's called constructing a normal probability plot. Now, a couple of things I just want to point out. Rarely will smaller data sets fit the empirical rule. It's really hard to get 68% of data to fall within one standard deviation if there's only 10 data values. 68% is just impossible to occur if you only have 10 values. I could have 60% or I could have 70%. Also, there's more chance variation in small data sets. That's why we typically like more data sets or more data values, because it typically allows us to have a more normal type of distribution. Now, in terms of the normal probability plots, our second method for assessing normality, the TI-84 or 83, even the 89, will make normal probability plots very, very quickly and easily. Now, I'm going to refer you to your textbook because they have step-by-step instructions along with an example of what to type in and what to put on your stat plot in order to graph the normal probability plot. Very, very straightforward. Please let me know if you have any questions. The key is being able to interpret these plots once you construct one. Now, if the points on the normal probability plot lie close to a straight line, the plot indicates the data is approximately normal. Deviations from a straight line indicate a non-normal distribution. Outliers also appear as points that are far away from the overall pattern. For example, if we have this scatter plot, what I could do is I could lay a transparent straight edge over the center of the photo and assess how straight the data appears according to that line. Now, even though the data doesn't fall in a perfectly straight line, it does seem to have overall somewhat of a linear form. The only substantial deviations are short horizontal runs of points, for example, right along here and right along here. So please don't overreact. Real data almost always shows some departure from the theoretical normal model. When you examine a normal probability plot, look for shapes that show clear departures from normality. Don't overreact to minor wiggles in the plot. If it's not normal, then what do we do? If it's approximately normal, it'll look linear, but if your normal probability plot appears to have some sort of curve, there's a couple ways to tell what the shape actually is. If you draw a line through the smallest points, meaning the points on the left side of the scatter plot, if the larger points fall above the line, it's skew right. If the larger points fall below the line, it's skew left. Now, I had a student teach me a little trick about this last year. They said, envision yourself driving. Your blinker is on your left hand, and imagine if you are turning right, you push your blinker up as you turn right, which is how they remembered that if the points fell above or up, that it was a skew right distribution. Now envision yourself driving and you're going to turn left, you push your blinker down. So if the larger points fall below the line or down, then the distribution is skew left. It's a little trick that a student taught me last year. For example, if I draw a line through the leftmost points of this scatter plot, the larger observations fall systematically above the line. So once again, I'm envisioning myself driving. If I push the blinker up, it's going to be skewed right. I'm turning right. Now example 3, I draw my line over it, and notice that it makes it clear that a normal distribution is a good description. There are only minor wiggles in a generally straight line pattern. Hope that helped not only in terms of how to assess normality, but also how to interpret normal probability plots. Once again, I suggest you go to your textbook, and Technology Toolbox is on page 153 on how to make normal probability plots on your calculator. And as always, please let me know if you have any questions or concerns. This is the homework assignment for students that are in fact in my class. And otherwise, have a great day.